Section: Introduction. In this section, we discuss the rise of advanced large language models, LLMs, like OpenAI and DeepSeek-R1, which have shown impressive reasoning skills in areas such as math and coding. These models use reinforcement learning, RL, to tackle problems step by step with a chain of thought, CoT, approach, improving the accuracy of their answers. This CoT reasoning has also been applied to visual tasks. Recent large multimodal models, LMMs, can analyze images alongside related text, allowing them to perform detailed visual analyses and combine these with reasoning to produce answers. We note that CoT-like reasoning has begun to be explored in visual generation, particularly in generating images from text. The initial work in this area treats the step-by-step creation of image components as a form of CoT, similar to how text is generated, and aims to improve image quality through this process. However, the application of CoT in image generation is still in its early stages. Unlike understanding images, generating them involves complex tasks like aligning different types of information and creating detailed visuals. To tackle these challenges, we identify two levels of CoT reasoning that can enhance image generation. The first, semantic-level CoT, involves reasoning about the image before it is created, helping to plan the overall structure, such as where objects should be placed. This level of reasoning can simplify the generation process by organizing thoughts before creating the image. The second, token-level CoT, refers to the detailed generation of the image in parts, where each new piece is based on what has already been created. This level focuses on finer details, like pixel arrangement, and optimizing it can improve the quality of the generated images and their alignment with the initial text prompt. Despite recognizing these two levels, we face a key question: how can we effectively enhance and coordinate them for generating images from text? Current generative models typically focus only on producing images, lacking the necessary understanding for semantic-level reasoning. While it is possible to use a separate model for interpreting prompts, this would increase costs and complexity. Recently, there has been a trend towards integrating visual understanding and generation in a single model. Unified LMMs, ULMs, can understand visual inputs and generate images from text, but these functions are often trained separately, with no clear benefit to the generation process from the understanding capabilities. To address these issues, we propose to enhance a ULM by integrating both levels of CoT into a single framework for text-to-image generation. We introduce BiCoT-GRPO, a reinforcement learning method designed to optimize both levels of CoT together. We choose RL over supervised fine-tuning for two reasons. First, the ULM already has the basic abilities needed for both levels of CoT, and we aim to encourage the combination of these abilities through guided exploration. Second, RL has proven effective in improving reasoning skills, which are crucial for both levels of CoT. Our approach involves first guiding the ULM to plan the image based on the prompt to achieve semantic-level CoT. We then use this planning as a basis for generating the image in the token-level CoT. We generate multiple images for each prompt and calculate a group relative reward to optimize both levels of CoT simultaneously. Since image generation lacks clear reward rules, we propose using a diverse set of vision experts as reward models. This design allows for a comprehensive evaluation of generated images and helps prevent reliance on a single reward model. Through these strategies, we present T2I-R1, the first model that enhances text-to-image generation by combining both levels of CoT. Our results show that this approach outperforms baseline models by significant margins on established benchmarks and even exceeds the previous best model, Flux.1. Qualitative analysis indicates that our method enables the model to produce results that align more closely with human expectations and shows improved performance in unusual scenarios. In summary, we identify a dual-level reasoning process in image generation, separating high-level planning from low-level detail generation. We develop BiCoT-GRPO to jointly optimize these reasoning levels, integrating the understanding capabilities of ULMs. Our robust reward system, based on an ensemble of vision experts, supports this optimization. The resulting model, T2I-R1, demonstrates substantial performance improvements and surpasses Flux.1 across various benchmarks. Section Summary. In this section, we explore the integration of two levels of chain of thought, CoT, reasoning, semantic level and token level, in text-to-image generation, addressing the challenges of aligning high-level image planning with low-level pixel generation. We introduce BiCoT GRPO, a reinforcement learning framework that optimizes both levels of CoT, resulting in our model T2I-R1, which significantly outperforms existing benchmarks and enhances the quality and alignment of generated images. Section: Related Work. In this section, we discuss related work on unifying image generation and understanding within a single large multimodal model, LMM. Recently, there has been significant interest in this area. Since large language models, LLMs, are already adept at understanding images and generating text, it makes sense for LMMs to do the same. However, the process of generating images from an LMM is still being investigated. We see two main approaches to image generation. The first approach uses an external image generation model, often leveraging text-to-image diffusion models because of their strong capabilities. In this case, the LMM provides either implicit features or explicit prompts to guide the generator. For instance, EMU trains the LMM to produce clip image features that match the input, which a pre-trained UNet from Stable Diffusion then uses to create an image. The second approach focuses on training the LMM to generate discrete tokens from VQGAN, which removes the need for an additional generator. However, since the VQGAN encoder is primarily trained for image reconstruction, it may not produce the best tokens for understanding images. To enhance understanding, some propose using different vision encoders for understanding and generation tasks. The clip encoder is used for understanding images, while the VQGAN encoder handles generation. Additionally, some efforts aim to equip the vision encoder with both understanding and generation capabilities. For example, VLA-U trains a vision encoder using both contrastive loss for understanding and reconstruction loss for preserving image details, allowing it to generate text-aligned visual tokens. We also explore the role of reinforcement learning in enhancing the reasoning abilities of large models. The work by OpenAI has sparked considerable interest in this area. DeepSeek-R1 introduces a rule-based reward system and a training method that encourages extensive reasoning before arriving at a final answer. The reward focuses on the accuracy of the answer and adherence to a specified format. Recently, this approach has been applied to multimodal LLMs with specific rewards for tasks like correctness and intersection over union, IOU, significantly aiding reasoning-intensive tasks such as solving mathematical problems and generating code. In our preliminary findings, we note that reinforcement learning has become a key method for developing reasoning capabilities in large models. The GRPO method enhances the proximal policy optimization, PPO, by removing the value function and estimating advantages based on group responses. For a given prompt answer pair, we sample multiple responses from the previous policy and evaluate them using a reward function to determine individual rewards. The advantage for each response is calculated by normalizing these rewards. GRPO also incorporates a clipped objective similar to PPO and adds a penalty term to the loss function to maintain alignment with a reference model. In text reasoning tasks, such as mathematical problem solving, we instruct the model to follow a predefined template for reasoning and answering. The reward functions are based on rules that check the correctness of the final answer and the output format. We also examine the concept of chain of thought, CoT, in autoregressive text generation tasks. Semantic-level CoT refers to the reasoning that occurs before image generation, acting as a planning stage for the intended image. This process resembles how artists conceptualize a scene based on a prompt, considering object attributes and relationships. We find that semantic-level CoT is beneficial in various scenarios, especially when the prompt is vague or does not directly describe the desired object. For example, it can deduce that tulips are grown in the Netherlands when prompted about flowers in Amsterdam. Without this reasoning, models like Janus Pro may struggle to produce valid results. Additionally, semantic-level CoT is crucial for interpreting unusual or ambiguous prompts, as it helps create coherent scenarios. Each instance of semantic-level CoT consists of a sequence of text tokens that guide the generation process. Section Summary. In this section, we explore recent advancements in unifying image generation and understanding within large multimodal models, LMMs, highlighting various methods that either utilize external generators like diffusion models or train LMMs to produce discrete visual tokens. We also discuss the role of reinforcement learning in enhancing reasoning capabilities in LMMs, emphasizing the importance of semantic-level chain of thought, CoT, reasoning for generating coherent images based on user prompts. Section: Token-level CoT. In this section, we discuss token-level chain of thought, CoT, in image generation. This process involves generating image tokens step by step, similar to how an artist fills a canvas, where each patch is created based on the previous ones. We refer to this sequential generation as token-level CoT, which focuses on local details and visual coherence, unlike semantic-level CoT that deals with overall planning. Each token-level CoT consists of a number of image tokens, where the total number corresponds to the image's resolution. Next, we introduce BiCoT GRPO, a method that effectively combines both semantic-level and token-level CoT in image generation. We first guide the model to perform semantic-level CoT for global planning, followed by a focus on local details through token-level CoT. However, integrating these two levels in image generation presents challenges, as many current models cannot seamlessly alternate between generating text and images. To address this, we manually add an image start token to signal the model to begin generating image tokens. Our proposed pipeline consists of two steps. The first step involves generating semantic-level CoT based on the image prompt, while the second step uses this output, along with the image start token, to generate the actual image tokens. Each response from the model includes both semantic and token-level components. We then update the model by maximizing a specific equation, incorporating a token-level policy gradient loss to balance the rewards. We also discuss the ensemble of generation rewards. Unlike rule-based systems, evaluating images based on predefined criteria is complex due to various factors like aesthetics and object relationships. To tackle this, we employ a group of vision experts to assess the generated images from multiple perspectives, using different reward functions to avoid reliance on a single model. Additionally, we consider using an object detector, such as grounding Dino or YOLO World, as part of our reward model. These models can identify objects in an image and provide their locations and confidence scores. We extract objects from training prompts and query the detector to evaluate their presence in the generated image. We assign binary scores for object existence and calculate spatial relationships when necessary, determining rewards based on these evaluations. We set a specific threshold to ensure the accuracy of spatial relationships, encouraging correct object positioning. Section Summary. In this section, we introduce token-level chain of thought, CoT, for image generation, where image tokens are created sequentially, similar to an artist filling a canvas, ensuring local coherence. We also propose BiCoT GRPO, a two-step generation process that combines semantic-level and token-level CoT, and discuss the use of an ensemble of vision experts and object detectors to evaluate generated images based on various criteria, including object existence and spatial relationships. Section: Visual Question Answering Model. In this section, we discuss our Visual Question Answering (VQA) model, which is designed to answer questions based on image inputs. Our VQA models include earlier versions like BLIP and GIT, as well as more recent models such as LLAVA. We utilize these models to assess the presence and characteristics of objects in images. For instance, if the image features a red dog and a yellow cat, we first rephrase each object with its attribute into a question for the VQA model, asking if there is a red dog and if there is a yellow cat. We then note the model's probability of answering yes and no for each object. Next, we implement an output reward model, ORM, that we fine-tune from an LMM, specifically LLAVA1 vision, to evaluate how well the prompt matches the image. This fine-tuning guides the model to respond with yes when the image aligns perfectly with the prompt and no otherwise. We calculate the reward from the ORM using a similar method as for the VQA, but we input the entire image prompt instead of rephrasing it. We can select one or more reward functions and average them to determine the final reward for a sample. Our training dataset consists of 6,786 text prompts from the T2I Comp Bench training set, without any images. Before training, we use GPT-4o Mini to identify objects and their attributes from the prompts to help compute rewards. We base our model on Janus Pro 7b, using a learning rate of 1/1,000,000th and a beta of 0.01. For the reward model, we select HPS as the human preference model, grounding Dino for object detection, and Git for the VQA model. We also fine-tune LLAVA1 Vision 7b for the ORM. To validate our method, we test on T2I Comp Bench and WISE. T2I Comp Bench includes 6,000 compositional text prompts across 3 categories and 6 subcategories, while WISE has 1,000 prompts covering 3 categories related to world knowledge. We slightly adjust the reasoning instructions for WISE to improve alignment with our results, adhering to the official evaluation settings for both benchmarks. In our main results, we compare T2I-R1 with leading text-to-image models on T2I Comp Bench and WISE. Our method shows significant improvements over the baseline, with average gains of 13% on T2I Comp Bench and 19% on WISE. The most notable improvements on T2I Comp Bench occur in attribute binding, with a 19% average increase. For WISE, the enhancements are more evenly spread across categories. When compared to advanced diffusion models, T2I-R1 achieves equal or better results on both benchmarks. Specifically, on T2I Comp Bench, we excel in 5 out of 6 subtasks, particularly in the spatial subtask, where we exceed previous state-of-the-art results by over 5%. Similarly, T2I-R1 leads in 4 out of 7 subtasks on WISE, achieving the highest overall score. Our improvements on T2I Comp Bench stem from the planning capabilities of the semantic-level chain of thought, CoT, which helps design complex scenarios before image generation. The enhancements on WISE arise from the reasoning abilities of the semantic-level CoT, which deduces the true object or location described in the prompt. The token-level CoT is crucial for accurately following the design to create visually appealing images. Without the semantic-level CoT, the model struggles to understand the depicted object or place, leading to misaligned results. Similarly, the absence of the token-level CoT results in various artifacts in the images, indicating lower quality. Section Summary. In this section, we describe our Visual Question Answering (VQA) model, which utilizes both earlier models and large multimodal models, LMMs, to assess object attributes in images, and we implement an Output Reward Model, ORM, fine-tuned for prompt image alignment. Our training leverages a dataset of text prompts, and we validate our method against benchmarks, achieving significant improvements over baseline models, particularly in attribute binding and reasoning capabilities, leading to superior performance across various tasks. Section: Reward Analysis. In this section, we experiment with different reward functions and their combinations to gain insights into how to select and combine them effectively. Our results are summarized in a table. We begin by testing individual reward models. The HPM model shows strong performance in attribute binding but struggles with object relationships, likely due to its limited understanding of relationships. The object detector model shows the least improvement in attribute binding, which is expected since it does not focus on evaluating attributes. Any gains come from better object detection in the prompts. We find that both the VQA model and ORM are effective, with VQA excelling in attribute binding and ORM in object relationships. Next, we explore combinations of reward models, starting with the HPM and object detector combination and gradually adding more models. Our findings reveal that both the HPM object detector combination and the integration of HPM, object detector, and VQA provide balanced results in both attribute binding and relationship modeling tasks. To determine the best reward models, we conduct a human study to assess visual quality. We select 4 reward model options to generate images from the same prompt and ask participants to rank and score the images. We randomly choose 30 prompts from various subtasks in T2I comp bench. The results indicate that ensemble rewards yield better visual quality, with the combination of HPM, object detector, and VQA achieving slightly better outcomes. This improvement likely stems from the regularization effect of multiple rewards, which helps avoid overfitting to a single model. In contrast, individual reward models do not provide satisfactory quality despite high benchmark scores. Therefore, we choose the ensemble of 3 reward models for our final model. In the ablation study, we validate the effectiveness of both semantic-level and token-level chain of thought, CoT. We first compare the semantic-level CoT with a baseline that uses only token-level CoT optimized with the GRPO method. The results show that semantic-level CoT generally improves performance across both benchmarks, with significant gains on the WISE benchmark due to its reasoning capabilities. Our method effectively reasons about the objects or phenomena in the prompt, enhancing the reasoning and generation processes for better results. We also notice that training solely with token-level CoT reduces the diversity of generated images. To measure this, we evaluate image diversity using the Venn score across 10 images generated for each prompt. The results indicate that training without semantic-level CoT lowers the diversity score, while incorporating it significantly enhances diversity through varied textual planning. We also examine a scenario where semantic-level CoT is used in image generation, but only the semantic-level CoT is optimized without the token-level CoT. The results show that optimizing only the semantic-level CoT yields smaller improvements compared to joint optimization. Additionally, images produced by optimizing both CoT types have much better aesthetic quality than those optimized with only the semantic-level CoT, highlighting the need for joint optimization of both levels.